on eClass. So all you have to do is just to follow that, and then you're gonna have to use that link to go into the waiting room. And as soon as I see the message that you're waiting, if there is no one else waiting, I will let you in. If there is someone else, so you have to wait until that is gone, and then I'll let you in and we can talk. So there are two people that you have to keep in mind that are going to help in this course. One person is the person who's going to help you with the marker, with the assignments. It's assignment marker, Mr. Mohammed Daryai. This is his email. So if you had any question regarding assignments, all you have to do is just email him directly. So don't send me emails regarding those. And about the projects that I'll talk about, if you have specific questions, you can also ask this guy, Mortaza Steki. And if you couldn't resolve it with him, you can always reach out to me and we can discuss it. So the prerequisites for this course, the courses that you should already know very well, are these courses. 401, which is Power Electronics. This is a very advanced course, which is built on top of Power Electronics. So if you haven't passed Power Electronics, you're gonna have serious difficulties grasping anything we're discussing here. And I do recommend you to drop the course, and even you can even register for this course if you haven't done so. So we're assuming that you know all those basic power electronics, and now we're trying to go into the more details, more advanced analysis, and how to analyze more complicated converters, simulate them, and design them. So you definitely need this course. And I've seen many people who think that, they can just catch up and read and that. This course by itself is really heavy. And if you haven't passed this course, it's going to be impossible. And it will be clear very quickly that is not possible to follow up. And all the projects and everything that you're going to get in this course, they're going to be personalized. So your project is going to be different from any other person. And because of that, it's going to be really hard for you guys to do this alone without these backgrounds. So I can't emphasize enough. If you haven't passed basic power electronics, just drop the course and change it, because it's not going to be, you're going to have difficulties. The other courses that are also very important are control systems, and also something that is missing here, I don't know why, is electromagnetics. Electromagnetics, about 30-40% of this course will be about designing magnetic components. So it's like inductors, transformers, especially for high frequency power supplies. So that's also advanced course on top of electromagnetics. So if you have any difficulties in that, you should again, think again and drop the course and get the prerequisites first. So in a lot, after almost half of the course, the mid course, you're gonna have to design a lot of magnetic components, and you're gonna need all those basic backgrounds. And there will be some references and textbooks, but basically what I've done here is collecting a lot of information from different resources. And that I've put some of them here, which is like the 401 course notes that we teach here. So this you can access them, take a look at them, and that's why one of the reasons I don't start this course right now. Formally, the details of the lectures will be done next week, is because I want you to take a look at those course notes, 401 course notes on eClass, and refresh your memory so that we don't have any difficulties getting started. The other books that are also important, and we'll be referring to them, we'll be using them from time to time, is Ericsson Fundamental of Power Electronics, and also Ned Mohan Power Electronics Converters and Applications. So these two also, some parts of these books are used, and then the rest of the course are taken from, journal papers and also from other resources. So there's no single textbook that you can just go and read. You have to follow the lectures one by one. There are some other PDF, other textbooks that are also here, just in case when I teach something, you don't understand it or you don't feel comfortable. You can also go through all these books and see if you can find any complementary topics and read them so you feel better about it. Any questions so far? Again, you can type in your questions or you can just unmute yourself and ask the questions. Questions so far? Is there anyone here who has not passed the power electronics and electromagnetics? So everyone has the background. Okay, great. So the assignments and projects. So this year, because we don't have any final written exam, we're going to have lots of projects and assignments. Okay, let me see. What was the course number for electromagnetics? Electromagnetics, I don't recall the exact number. I can correct this slide and then put it on eClass and you can see it. But electromagnetics 1, just the basic ones, the meaning, the definitions of, flux density, flux intensity, and all those things. Yeah, probably ECE 370. Which software knowledge required to perform. So any software that you can simulate converters is going to be fine. MATLAB or PCM, those are the ones that come to my mind, but any other software that we can use to analyze a simple converter, it should be fine. I don't care about those, but I think if we can use MATLAB, power converter toolbox, that would be the best, so that you can also easily ask help from the TAs of the course. Because if you use something random, it's going to be hard for them to help you or debug your code and take a look. So I do recommend, if you have access, use the MATLAB toolbox. All right. So the assignments, you're going to have 30% assignments. So we will have a few assignments. I don't recall exactly how many. We'll see. The due dates of these assignments is going to be two weeks after the post date. So these are like just some problems and questions that you answer, and then just submit on eClass. The instructions will be given how to do those. The term, we have a term project, and then we have a final course project. So the term project is more comprehensive. It has several different milestones and steps. So we will guide you through all those. And I will explain in more detail in a second what this is. It will be 50%, and that's the part that you'll be in touch with the project TA, Morteza Esteki, and he can guide you through those. And if you have any problems, and it's based on what we're, you'll be given a starting point, and then you'll complete it as we go. The final course project is one converter design, complete converter design, which will be given to you in the last months of the course. And the last day of the classes, or I guess it's the week after the last day, is going to be the due date for the course project, the final course project. So the grades will be awarded based on relative performance. So whoever does the best is going to get A+, and then we go down from there. So first of all, if it's because we have all types of people here, we have MNG students, we have master students, and also we have PhD students. It's a little bit challenging for everyone to catch up, but you should do your best. And it's what's going to happen is that I will try to give you as much feedback as possible. But again, if you don't have the necessary background, because this is going to be evaluated based on relative performance, you should be careful, because you will be already at a very at a disadvantage position, because other people can be a PhD student who've been working on power electronics for some time, and now you don't even have the basic background to follow the course. But if you have those background, if you know power electronics and electromagnetics, you should be in a good position to follow the material throughout the course. For assignments, not all the questions will be marked. Only one or two of them will be marked, and they will be chosen randomly. So make sure you answer all the questions as if that was the only question that is going to be marked. So if you answer 90% of the questions and then you miss one, and then that one was just randomly chosen, so you're going to get a 0 mark for the whole assignment. So make sure you answer all of them completely, so you don't lose a lot. Any questions on the assignments and projects so far? No? All right. So let's talk about the term project. The term project is going to, the objective is to help you learn whatever we're covering in this course, which is analyze, design, simulate, and compare converters. So how are we going to do? We're going to give each one of you guys a converter topology. And, after like a couple of weeks, you should be in a position to start the term project, because you have the tools to start analyzing that converter. So this is separate from your assignment. So in this course, we're going to see different things like how to different converter topologies, how to analyze them, how to pick and select components. So as we proceed in a course, you're going to apply whatever you learn on that converter. That's the main idea. But what is going to happen is that we're going to get some kind of report in 4 separate milestones that we have throughout the project. And I'll explain what those milestones are, but it's the whole process is going to be you're going to submit 4 reports in this throughout this project. So a template will be provided so that you know what exactly you're supposed to do in that part for that report or that section of the report. And then you follow those and you try to fill out the report as you go. You will receive some feedback because every step, milestone 1 needs to be done to move to next milestone. So you will get some feedback and you will get a chance to correct it. However, when you submit the report and you were not able to do what was asked of you, you're going to lose some marks. But because it depends on the next steps, you're going to have some feedback and then you can correct it and then move on. And also because of this COVID situation, we understand that you might be isolated and you might need some help. These feedbacks are designed so that you can help you to move easily, move forward easily. And to answer your question that projects are individual, yes, the projects are individual. You can always discuss it with others because they're also doing a similar thing for a different converter. But you can discuss if you have difficulties in understanding some steps. You can always discuss it among yourselves. But overall, everyone's converter is going to be different. So you're going to have to do that for your learn it and apply it to your own converter and topology. Are there questions? All right. So, what are these milestones? In the first step, a basic converter will be assigned, and you should completely analyze it in steady states. And this is something that you'll learn in the first couple of weeks of the course. So that can be done soon. And in milestone 2, you will have 3 various desired specifications. For example, we may have a buck converter. This buck converter can be used in different applications. In one application, you want to go from, let's say, 10 volt to 5 volt. In another application, you may want to go from 500 volt to 100 volt. And in another application, you may have something else at a different power level. So 3 various specification is going to given to you, inputs, outputs, and power levels. And then you're going to design the converter that you've already analyzed in details. There might be some research component into it to find out how to design it. We will discuss some design procedure for basic converters. But then, the converters you're going to choose are going to be a little bit different. So you're going to have to do some research on how to design this converter and what makes sense or what not. And then design it for those 3-4 different specs and simulate them. And then the performance of the converter means how the converter is doing from gain point of view, how sensitive it is for parasitic components, and what would be the efficiency of converter. These should be, in detail analyzed for each one of those, specs that are given to you. And then in the next step, you will be given some instruction how to improve some aspects of the converter. And when you improve, so you're gonna make some changes in the topology. So now you're making up a new topology. And then after that improvement, you're going to do and repeat again 1 and 2, analyze it, and then design it for those specs. And then in the last part, you're going to compare all different things that you've designed for different specs. And this way you can learn that, okay, one specific converter might be suitable for some specific voltage level and power level. And if you want to go to extreme cases, you're going to have to do some improvement and modification in the converter and then make it suitable for that. And this is the whole idea of this course, so that you understand all those limiting factors that are not actually taught in the basic power electronic course. You learn the buck converter, that the buck converter can step down a voltage. But, okay, can we use a buck converter to go from, let's say, 48 volt to 1 volt? And we have that application, especially recently in telecommunication and other different applications that you need a very high step down converter. So if you need something like that, what is the problem with, let's say, buck converter? How can you modify it, and how can you make it better? And then you have to analyze and measure and find the performance of converter in all different specs, for all different specs. Is that clear? Is there any question about the milestones? Questions? So another thing about this course and any other course, don't be shy to ask questions. Normally what you have in mind is something that other people have in mind. So those courses that are interactive are going to be much more productive, and all people are going to be taking advantage of the questions. So make sure, ask questions. If you have any concern, just ask it. I'll try to clarify it. Especially with this type of Zoom lectures, it's very easy for everyone to get lost, and also for me it's going to be even harder when no one talks. It feels like I'm talking to myself to a computer. So it would be great if you could just ask questions and interact. All right. Questions? No? Still shy? All right. Let's move. One thing that I should mention, that all these things that we're defining, these are tentative, so they may change, they may be modified. This is what we have in mind right now, but when we do it, we may come to a conclusion that, okay, this is too simple or too hard, too complicated or too superficial, and we may add or remove parts. But overall, this seems like a good project for what we're going to cover in this course. So the percentage allocated to each milestone, this is again tentative. 15% milestone 1, 15% milestone 2, and 3, 30%, and the last one, which is the bigger one, is going to be 40%. And after each milestone, you're going to submit your reports, and then you're going to get some kind of feedback about what you've done, and if you need to modify it for next steps. Okay, now I'm going to finish the, talking about the logistics of the course. If you have any concern or questions, now's the time to ask. when the term project will begin. As soon as we get some basic material that you can do the first step. You can start the first step. So we'll see how things will move. But I think it's going to be second or third week. But you're going to have some assignments before that, for sure. So you're going to be busy, almost the first or second week, you're going to get some assignments to do. So the second question is, so the final project will be a separate project or is it a combination? No, it's going to be a separate project. That will be one complete design of a converter from A to Z. The steps will be given again, but that will be a separate project. But this one is more like, practicing on what we're learning along the term. So it's a little bit different. That the last one is going to be, the last project is going to be an isolated power converter. And what you're going to start with is going to be non-isolated power converters. So there are going to be different topologies, and you'll learn different things in them. Are the specifications of term project are same for all students? Most probably they will be similar, but not exactly the same because converters are different and there might be some variations. So I haven't decided yet. I have to first know how many people we have and then see how many converters we have. And see how different the specs should be. Yeah, any other questions? All right. So when I say that the specs are going to be different, it doesn't mean that one of the students is going to get a more challenging spec or something. No. So we're going to give them almost a fair, level of complexity for all students. It's just because converters are different, their potentials are going to be different, so the specs are going to be different. But within the potential of each converter, we're going to ask you to design that converter for extreme cases. For example, let's say a boost converter. Okay, so how much can I boost? Can I get infinite gain? Probably in theory, yes, but when you really consider the parasitic components and other things, you'll see that there's a limit. So now, does it depend on power level? So if that's yes, for different voltage and power level, how can I design this boost converter and what is the best performance I can get out of it? So that's going to be different from a buck converter, right? So the buck converter will have some limitations, but in a different spec range. So that's why these are going to be a little bit different, but most of the challenges and steps you're going to take are going to be similar to each other. It's just you're applying it to different converters. All right. So there's no other questions. So here's what we're going to cover. The course outline. So we're going to review some very basic things very quickly, waveforms, power calculations, and this is just to make you familiar with the way we're going to talk and discuss throughout the course, because the notations are coming from different backgrounds and everything might be different. So this is where we're going to just, quickly review this and say that, okay, the convention we're using is this. That's how we're going to do power calculations and converters, topologies, and all those things. Then we will talk about non-isolated DC-DC power converters. We'll talk about basic topologies very quickly, and then we'll talk about derivations of these topologies. How can I change that topology and I can derive other topologies? Then we will talk about operations and steady-state models. These are also things that you've seen in power electronics, some of these, but here you'll see a more formal, way of analysis. So the steady-state analysis that we cover, we'll teach, will be something that you can apply to any converter. So it's not just specific to one type of converters, and that's how you're going to use that methodology and apply it to your own converter. And then you can get some dynamic models out of your converter. So after you're familiar with topologies and converter basic analysis, we'll talk about switching devices. Okay, so now we have the switching devices in each power converter. What are the characteristics? What are the differences between a real and ideal switch? We'll get into the details of a MOSFET to physical electronics and switching loss calculations. The switch loss calculations that you've seen in basic power electronic courses are too simplified, too simplistic. And here you're going to see a more detailed of loss analysis. What exactly happens when you turn on a device, what parasitic components are charged and discharged, and what is exactly happening inside a MOSFET. And then you use those to calculate the timings of MOSFETs, switching actions, and then you'll be able to calculate the switching losses and the conduction losses and all those things. So this is a good opportunity to actually get familiar with all the details of the switching devices, specifically MOSFETs that we're covering here. And then we will talk about some of the reactive circuit elements or components, like capacitors and inductors. Sometimes due to restrictions of time, we may or may not cover the capacitors. We'll see how it goes. Capacitors are not that challenging. I can just post the lectures for that in case you need it for your project and other things. But inductors and transformer selections and designs and all those details, that's again, it will take at least 2-3 weeks that we will talk about those details. So we will dive into the details, go to the electromagnetics, what are the flow charts and steps to design this. We will talk about the loss mechanism inside the transformer, high frequency losses like eddy, proximity, and all those details. And we'll see how to estimate these so that you can have some basic estimations for your magnetic design. And at the end, we will have a short presentation on DC-DC, isolated DC-DC converters, and what are the topologies. And we won't talk about soft switch converters or resonant type isolated converters, but we will talk about some of the simple soft switch converters and isolated converters, the operation and steady state models. And then you will use whatever you have. You'll use whatever you have learned. Let me see. You'll use whatever you have learned to do your final project. You can apply all these techniques and things that you've learned, and you'll design the power converter that you've given. Any questions so far? Questions? No. All right. So let's talk about power converters and see what they are, why we need it, and we'll talk about some basic applications today. So the objective right now is just to remind you and talk about different applications that we have for power converters and understand the background a little better in a more broader, point of view. So if you're thinking about conversion, power conversions are actually converters are used for these power conversions to go from one form of energy to another. So let's say you have AC system and you want to create some DC. So this is called rectifiers. If you're changing the voltage from AC to DC, it's called rectifiers. It can be uncontrolled, as you've seen it in your power electronic courses, or controlled, like uncontrolled are diode bridge, and control rectifiers can be bridges with thyristors, for example. And those are called rectifiers. If you go from DC to AC, so it's from DC to AC, what you're going to see is, what you're going to get is inverter. By the way, can you see the mouse, the pointer that I'm moving here? Do I need to turn on a pointer, or you can see the mouse movement? Very small. All right, let me see. Is it better now? Yes, okay, great. All right, so the inverter is the one that converts the DC to AC. And if you go from any DC to DC, we just call them converters, non-isolated, non-isolated, and resonant converters. These are also called converters. These converters, the term converter can refer to all types of converters, right? So a rectifier is also a converter, but the DC-DC converter is specifically called a converter. And we also have AC to AC. So directly we go from AC to AC. It's like a matrix converter or cycloconverters or AC converters. These are different terms and types of AC to AC converters. So in different courses that you take at University of Alberta, they're going to focus on some of these converters. For example, in Yasser's, Dr. Yasser's course, he's going to be talking about inverters mostly. And Dr. Ryan Lee, he will be mostly talking about inverters and some of the DC-DC and AC-AC. So depending on the course material, you may see different types of converters. In this course, we mostly focus on DC-DC, but we will be talking about different types of converters as well, because although we focus on DC-DC, what we're teaching here can be applied to any converter. And it's not going to be too difficult to apply these techniques for other types of converters. So what is one converter? So a one converter is a power processing unit that has some input. So it takes some power from input and it provides some power to the output. But the voltage and current at the input, the form can be different. It can be DC here and different at the output. So, but what it does is processing this power and change it to another form that we want. But why do we need these power electronics and converters? These converters can actually be convert the power from one form to another. So if you have AC and DC, as we discussed, you need some kind of conversion in between. These type of converters provide additional control and optimization on power extraction, on the power flow, and also the consumption, as well as power quality and cost. So what does it mean? When we put a controller here, we're sensing something in the system, and then we decide how far we are from our desired value, and then we change something in the converter. We send a command to the converter so that we get that objective. So this control aspect is actually very important, because let's say you want to go from 10 volts to 5 volts. You're using a buck converter. So the buck converter is going to be converting at a duty cycle of 0.5. You're going to go from 10 to 5. So why do I need a controller? If you really want to stay at 5 volt at the output, and no matter how much current your load is drawing, then you definitely need a controller. And the reason is that as soon as you start drawing the current, all the parasitic components in your power converter will come to picture, and will drop your output voltage. So the higher the current, the output voltage is going to be lower. But now you really want to make and try to fix the output at 5 volts. So you need a controller, and you have to change the duty cycle as this disturbance is creating problem for you. And the disturbance is the output current. So you almost always need some kind of closed loop system in power converters. And that's another reason. And in many cases, you may be able, in theory, to find some open loop just topology that does it, but in reality, you always have to have some kind of optimization and controller to get to that level. So that's why that's another reason that we need power electronics and converter. So the other reason is to match the voltage and current level of the input and output, the source and the load. So the source might be your grid. You have 120 volts at home, and your computer motherboard is going to need 1 volt, 3 volts DC, and it is going to need it at very high current. So how can you do that? If you you need something in between to convert that AC to that DC, but with a specific optimization and control that the load needs it. Also, the source, that power converter is going to make sure that you don't draw full of harmonics, current from input. So again, that power converter and this control signal will sense the input current, will sense the output current and voltage, and decide how to change the variables so that all the objectives are achieved. And these are the objectives that normally you have. So the question is, how can we find these lectures on eClass? Yes, after I'm done, I'll post the lectures on eClass. And next time I'll do my best to post the lectures right before the class, probably a few hours before the class. Okay, any other questions related to these ones? No? All right. So what's the difference between linear regulators that you've seen in, let's say, electronic courses and switch mode power supplies? And those are the things that we discuss in power electronics. So in linear power supplies, you have a load, you have a source. The load needs 25 volts. What do? They put a transistor in between, and they change the bias of this transistor, so the equivalent resistor of this switch is set so that you get half of this voltage at the output. So it's clear you're going to have to set the resistor resistance at exactly equal to our load. So what does that mean? If you're drawing, let's say, 100 amps here, 100 amps times the voltage that is applied here, which is 25 volts, is 2.5 kilowatt loss on this transistor. So the efficiency is going to be, for this case, is going to be 50%. So that's why in high power applications, these linear power supplies are not going to be useful because the losses are just going to be too much. So what do we need? We need 99% efficiency. That's what we're trying to get. That's what we are right now, actually, in reality. Many of these power converters that are designed now can reach 99%. Of course, this is very, very challenging task to do, but it's being done. And it's very, very large research groups, and everyone's working on just increasing this the efficiency that they can. But how can they reach that? A switch mode power supply is doing that conversion a little bit differently. So that switch that we had there, assume that that switch is turned on and off at a duty cycle. And duty cycle means a portion of the frequency of the switching for a portion is on, for the rest is off. So the on time over the period, that's called the duty cycle. Okay, so the duty cycle of this switch is going to determine how this VI waveform is going to look like. So if I switch it like this, at these times, I turn on the switch, so I get exactly the same voltage at VI, and then I turn it off at this stance, so I get a zero voltage here, right? Let's say I have another switch here to make sure that this gets zero, or the filter makes this zero. So now I get two-level voltage here. If I apply a filter, a passive filter, so that it can take the average of this voltage and apply it to the load, the average of this voltage is going to be this. So if I set the duty cycle to 50%, I'm going to get exactly half of the input voltage at the load. So in reality, because I'm turning on and off this ideal switch, I'm not going to get any loss, because this switch, when it's off, there's no current. And we know the loss of a switch or any component, the power that is going to any component, is the multiplication of the voltage and current. So if I multiply the voltage and current of this switch at any instant of time, I always get zero, because either the current is zero, the switch is off, or when the switch is on, the voltage is going to be zero because it's short circuit. So this switch, if it's ideal, is not going to have any type of losses. And the MOSFETs that you have right now, for example, they're very, very close to ideal. So the on-time losses, the on-time resistance can be fully on, right? The fully on resistance can be like milliohm, and the fully off resistance can be hundreds of mega ohm. So you don't have any losses. But here, because I was working in a linear region, I had to get something between, not milliohm, not mega ohm. I had to make that resistor exactly equal this load resistor to get the half of the voltage. That's why the resistance here was not something that I could avoid. But here, even with the same switch, I can go from fully on to fully off. So that way I don't have any losses in either cases, and I can get a zero power losses. But in practice, because you have lots of losses around the circuit, if you are not very careful, you can get, 90%, 80% efficiency. But if you are careful and you know what you're doing and you design it nicely, you can easily get 95%, 93%, 4%. And if you work very hard, you can reach almost 98, 99% efficiency. And you may think that, okay, who cares about that 1% loss? Just imagine you've purchased a power converter for the roof of your house to convert the solar energy to electricity. So that is the source of income for you, right? So over time, this solar inverter is going to be on the roof for, let's say, 20 years. So if you're always losing 1% efficiency, the power that you're getting for free from the sun, but it's not free to convert it because you have to buy and invest on the converter. Now you're losing that 1% over 20 years. And if you just calculate that, you'll see that even one person in a residential application is losing a lot of money. Now, these power converters, as we will see today, are going to be used in so many different applications, and in low power, high power, in utility applications. And when you multiply megawatts in the converter's efficiency, you'll see that loss is going to be very significant. And the other problem that these losses are going to create is the heat. That heat is going to heat up the converter, is going to create lots of problems, and how you have to make the converter big enough so that you can dissipate that heat. So all those things will limit the size and how compressed you can make your converter. So all these things will show how important it is to how important the efficiency is. And that's why throughout this course we will be talking about a lot of things, but many of them are related to efficiency. How to improve efficiency. What is the best converter for this application to get the highest power output or highest efficiency out of the converter. Any questions so far? Questions? No? Okay, what time is it? I hope I'm not going too fast. We started 2. Okay. In 10 minutes we can or maybe we can get a rest, a break about, let's say, 5 minutes and come back, because I need to drink a little bit of water, and that also gives you a little bit of time to rest. Okay, so I'll start again in 5 minutes. Let's take a break. All right. So, is there any question for me here? Yeah. So the MATLAB Power Toolbox or something like that. That's called. We'll get to that. I'm not sure. So let me first find out as a student here what you have access to, and then I can tell you what to do and how to do it. So don't worry about it right now. We will talk about this these things later. About the Plex, you could, but as I mentioned, because you're going to need the TAs to help you, it's probably better so that everyone uses the same thing so that he doesn't have to go back and forth in different simulation tools and everything. And I personally don't have, don't have the license for Plex. I don't know if he has it or not, but I do recommend that everyone uses the same thing. So let me figure that out in the next couple of weeks, and I'll let you know what is the best solution to this. But I'm guessing the MATLAB Power Toolbox is going to be enough. It has all the things that you need, and I suppose you guys as students here should have some kind of access to it. So let me figure that out, and then I'll let you know. Other questions? No? All right. So let me share the screen again. For some reason, I'm not seeing the chats anymore. Where did that go? The polls and control, optimize, hide. For some reason, the chat is not coming up. Oh, okay, it came. Okay. So let's continue. So any other questions before I start about the technical specs discussed? Okay. All right. So in reality, a switch mode power supply, it has a block diagram like this. So if you look at this, for example, this is the power processing unit, right? And this is the controller. So the input, and this is the output. The input in this case is AC, the utility, the grid, and the output is the output voltage, right? DC. So can we go directly from there to there? Probably not. You need different stages. So you're going to need some rectifier. You create a high voltage here, and then you use some kind of switching actions and topology and a transformer. So you convert that high voltage to some kind of AC. So you can use high frequency AC transformer. So the size of this transformer, because it's high frequency, is going to be very small. And then you're going to rectify that ECE that you created. So from using this transformer, you can go, let's say, from 400 volt to 10 volt with just tens ratio. And then you turn back that to DC and filter it. And then you get a pure DC output here. And when I say pure, almost pure, because you always have some kind of ripple. So how does this control loop is closed? You have a voltage. Let's say you want to go to 5 volt, 10 volts. So the 10 volt reference is here, but the output, the actual output right now is fed to the controller. Let's say this is a PI controller. It sees that these are different. It starts to create, to increase that duty cycle. So more energy is converted to output and increases the output. So that's how this loop is closed. What makes it difficult from a control engineer point of view is that everything that is happening here is nonlinear. You have switching actions, you have lots of nonlinear components. But when you want to design a controller for this, you mostly want to use a simple, a linear type controller. And to analyze and model this in terms of controllers is not going to be very straightforward. Sometimes at the end of this course, actually, I also talk about controllers. We'll see how fast we can move in some classes because they are very interactive. We talk a lot. Many questions are asked. We get more into the details and we clarify a lot of things. And sometimes when there's no questions, the pace of the course becomes faster, and then we will have time to cover more on the controller. So then we can have some assignments on the controller part also in your final course project. So, but let's see how it goes, if we have time at the end or not. So a converter here is converting AC to DC. It has different stages. We will talk about these in details in this course. But what does it look like? It would look like something like this. This is a MacBook charger. MacBook charger, is a very small charger. But inside, you're going to see all those stages that we described. So you connect it to AC here, and first you have some EMI filter. Make sure that this, because of the switching actions that are happening inside, doesn't create noise that goes to other devices and creates problems for them. That's EMI, electromagnetic interference filters. And then you will have some bridge rectifier and the filter and the boost converter. These are all the power factor correction unit. It's called because you want to create some AC current here. When you're drawing power, you don't want a very distorted current drawn from the utility, because that distorted current is going to create lots of losses on the grid. You don't want those losses. How do you do that? You're going to shape the current like 60 hertz or 50 hertz sinusoidal waveform. And that's what the power factor correction circuit does. So this boost converter that they have here, or in our case that in the previous converter that you have here, this is a forward converter. So here you also have this converter that you can shape the current here. So you can shape the current like sinusoidal and then rectify it. But because of this capacitor, that's not actually possible. So this is not a very good, converter in terms of input current harmonics. Anyways, here they have this PFC, and then the next stage, you have another stage to convert this whatever voltage at the output of PFC you get to a converter to AC and pass it through the transformer, and in the transformer you can have any transistor you have to convert it to any voltage level that you have. Probably this is a resonant type converter they've used here, and then the output will go to DC, and it will be going through this to your computer. So this is how your battery gets the voltage and current that it needs to get charged. So do we want to have all these components, and is it small enough? For the time it was built, probably yes, but these days they're trying to make it so small that they fit in the plug that you have. So you don't have anything extra carrying around. You can just, whatever plug you put there, the output can be the DC you have. So that's how small they're trying to make it. But this is already too complicated. Can you go further integration? Yes, everyone's moving toward that, but how fast it's going to happen, we'll see. So based on what I explained, you can see that power electronics is not just about converter topologies. It's a very complicated, multidisciplinary area. And you can see that, in power electronics, where you're working with this type of converters and power supplies, you're going to need circuit theory, you're going to need system and control background. You're going to have to do signal processing. For example, if you're dealing with the grid, with the 50 Hz, the harmonics that are coming there, lots and lots of signal processing, over there, and the DSP or microcontroller you're going to use is going to do all those kind of calculations and analysis. You're going to need lots of electronics, the A to D, D2As, and all, sampling and everything that you have here involve a lot of electronics. And you're going to know a lot of, you're going to have a good background in electromagnetics because you're going to design this. One thing about magnetic component is that most probably you're going to have to design it or custom design it, because unlike the capacitors that you just go and take a look at the capacitor spec, there's a few categories, but you can find most probably what you want, off the shelf. But magnetics, you have to custom design it for every circuit, because the current level, power level, voltage level, frequency, everything will change the magnetic design. And that's why the variations are so many that they can't just give you all different possibilities. There are some pre-designed magnetics, but they're not very wide. There's some, they just cover some, specific applications, specific, very common applications they design it. But if you really want to design some good power supplies, and you have to get into the details of electromagnetics. You should know about power supplies, power systems in power supply design, because you have to know how to deal with this utility, how to deal with the interaction of the converters and other power converters, other components of the grid. So that is also needed. Electric machines, if you're designing this power electronics for electric machines, you have to have a very good knowledge about electric machines, because this is going to control the electric machines. Simulation and computing, that's also very, very important. It becomes more important every day as you're trying to push the frequencies higher. For example, in our research group, we're doing megahertz design, and in megahertz design, it becomes very difficult to find the parasitics and calculate them and predict them. So we can do whatever we have, in the first step to design it, but then you have to simulate it like ANSYS or some finite element method with simulation software that uses those to actually understand exactly how these magnetic fields are going inside, how this whole thing are interacting with each other, how the switching actions are happening and losses are formed. And these things become very complicated and very important. And solid state physics for sure, because you're dealing with these MOSFETs and diodes and all those things, and you have to have a good understanding of the details of those, how they operate, what are the limitations, and which one to choose for your own benefits in your circuit. So as you can see, as a power electronic engineer, you have to have a very good understanding about almost all those important courses that you've done in undergrad. And that's why it takes quite a while for everyone who comes to this area to get to the level that they can actually build a nice working power converter. Any questions so far? No? So what are the applications? Of course, I'm sure you know a lot of applications for power electronics. Residential, we can find them everywhere, electronics, cooking, air conditioning, and all those things, they have power electronics. Commercial, lightings, computers, UPS systems, elevators, industrial. Again, so many of these machines are using power electronics. Transportation, these days we're talking about electric cars, and all electric cars, hybrid and all electric. All electric means all power electronic. So a car like Tesla is loaded with all sorts of power converters, different, in all different levels. Because as soon as you're dealing with something that needs power and it's electrical, it means you have some kind of power electronic there, either to control the power flow and operation, or to convert the power from one form to another. So take the power from, let's say, a battery and feed it to a motor. The motor can be three-phase AC. So all these things in between needs a lot of special design power converters. And utilities and aerospace, telecommunication. So basically, if you want to categorize them, you can see renewables, electric vehicles, power quality and efficiency for grid utility, information technology, lots and lots of converters in telecommunication systems, and utility applications. For example, HVDC, high voltage DC systems. They need power electronics to create that high voltage DC and for transmission systems. So here are a few facts to give you a better idea of what these power electronics and power converters are used for. So by 2030, is estimated that 80% of the power, the whole power of the world, will be processed through some power electronic systems. So 80% of the whole power. So it means almost anything that you see, there will be some kind of piece of power electronic converter. The total, just to give you some incentive, the total energy usage that we had in 2015 was 13 million ton whole equivalent, or MTOE, 13,000 million MTOE. So this translates to 17.3 terawatts of power during the year. So how much do we need renewables to produce this? If you have an area of 200 miles by 200 miles covered with solar panels, you're going to get 17.4 terawatt of power. So we can easily achieve this. It's not something that you think the whole power that we're consuming is so high that we can never reach with renewables or a source of energy. We have abundance of energy source. But the problem is these energy sources like the wind, the solar, these are all intermittent source of energies. It means you cannot rely on them. They're there for a second and they're not there for another. So this intermittency, this on and off, is the problem. How can we solve this? We're going to need a lot of energy storage. And if you have energy storage, then, even with just solar panels, you're going to be able to, provide all the energy that you need from the sun. So this gives you some perspective that what we have here, the power electronics, can be a solution for future. And will be a solution for future, a solution to this energy challenge. The only problem is how fast we can get to the energy storage that we need to store all the energy that we need and always have a necessary backup. And that probably is not too far in future, and we're moving toward there. And you can see that, for example, every year these electric cars, the energy storage is getting better, and they can go a few hundred miles, or not few hundred miles, a few miles more than before. So they're improving the efficiency, they're redesigning the whole thing, and also there are lots of advancement in energy storage. So it's getting there, but we still need a little bit more time to get there. Questions so far? So if we compare it, does it mean that fuel is hazardous to environment and solar is clean and green energy? Of course, green technologies are clean. They're not going to create lots of waste like fuel. But the problem is some people argue that, for example, the solar panels themselves, if you really want to create that many solar panels, they're not going to create pollution. They've done calculations, and I've seen them. They're nothing comparable to the waste and pollution that fuels are creating. So to answer your question, in my opinion, solar and plus energy storage is the way to go to resolve all this, pollution problem that we have right now. And that will create a lot of opportunities for many people. The oil industry is not going to end, is not going to stop, because oil has its own, usage. It's not just for gas, as a gas for cars. It's so many different things can be, in so many different ways it can be used. But it's just not very logical, in my opinion, just to burn it and create all the pollution with it. Yeah. Other questions? But at some same time, crude oil go through many processes. It is expensive. Yes, true. So crude oil is expensive. I'm not sure the reason is political or it's real. And it seems like it's not a real price. They can be very, very cheap, but overall, yes, if solar gets, very widespread and energy storage problem is solved, then the crude oil is going to be cheaper, and we're not going to have that much thing. Yeah, if we talk about solar, it is one-time investment for less maintenance, one-time investment for 20 years. After 20 years, they're going to degrade, you're going to replace it, and they're going to be better, higher efficiency solar PV panels. But I'm sure there are ways to recycle the panels, and it's going to be much more effective and less pollution with them. Yeah. All right. So let's talk about these systems a little bit, so you get some ideas what these power converters are doing. So if you look at a PV panel, a PV panel is one solar panel that you can buy, and the output of these panels normally are 200, 300, 400 watts. What are the characteristics? So if you measure, so they give you two ports at the output of these solar panels. It's like a battery, right? So if you have irradiation from the sun, so depending on what voltage you apply at the output of the panel, you'll see different characteristics. So we can see here that for different irradiation levels, your power is going to change, right? But at different voltage, this is the voltage of the output of the panel, you get different power levels. So, and there's one point, which is here, that for one irradiation, so let's say this is for 200 watt per meter, square meter irradiation. So for that, you get this much power, output power, let's say 40 watts. So depending on how good you can adjust this output voltage, your power, the power you're going to get from this PV panel is going to be different. So this is changing all the time, and it's a nonlinear characteristic, because as soon as you have cloud, you are operating here, all of a sudden you're operating here, right? Because the characteristic of a PV is changing. So that's where a power converter with intelligent control comes to play. It tries at any curve or at any irradiation, it will try to operate at the maximum upper point. It's called maximum power point tracking. So it will always try to get you at this point. This curves also change with temperature. You can see that if I reduce the temperature, actually the output power is going to be better. So if sunny places but cold locations like Edmonton, for example, is actually very good for solar farms and solar panels, because we get a lot of days throughout the year that are sunny, and the temperature is normally cold, so you can get, let's say, 40%, 50% more than, let's say, another place like Arizona that is always hot. You can see it can go 200 watts to almost 120 watts, right? So if temperature goes up, your power is going to go down. So the temperature changes, the radiation changes, the characteristics are always changing. There might be partial shading on the PV panels. So what can we do? We have different panels. Let's see what are the difficulties. In one model, they call it central inverter. They just connect these panels. This is one panel. This is or module. They call it module or panel. When they connect them in series, they call it the string. So when they connect all these in series and then in parallel, all of them together, and then they get a very high voltage, high power output, they can get one central inverter here. This central inverter can adjust this voltage so that the power that you're getting from all this is maximized. But let's say this panel is shaded. As soon as this one panel, let's say a bird is sitting on it, you would lose the power in all these strings. And to answer your question of how many cells in one panel, we have 60 or 72, we have different numbers. It depends on the technology the panel is using. But anyways, if one panel is shaded, then you get, because these are all in series, even inside those cells that we're talking about, that each one of them is like a diode and is creating 1 volt, 2 volt for you. Each one of those will actually are in series. So one of those cells, if it's shaded, it will reduce the power of this panel. It won't make it zero because it has 3 diodes that bypasses the internal part of internal cells. So let's say if one cell is shaded, you're going to lose probably 1/3 of this power and current. But if a panel is shaded, something happens, let's say you have some snow, all the snows are melted and only one of them is shaded, or early in the morning the sun is coming up, all having sunlight, one of them is shaded with a shade of a tree on it. So what's going to happen is that all the current in this string is going to go to 0 because this is all in series. So that's why this centralized inverter topology is not very good. To solve this, they can have inverters for each string. So now, if one of them is having a problem, this will try to optimize the voltage here, whatever is left. But over there, this inverter has no access to voltage and current of this individual string. So there are normally some diodes here. As soon as that happens, that diode turns off, the whole string is going to be out. But here, this at least will try to get as much as it can from the rest of this remaining panel. But again, this is not optimal because this panel is, if one of them is shaded, it's going to affect all of them. So we can have a module integrated inverters, or they're also called micro inverters. So micro inverters is one inverter connected to one panel, and the output of these inverters are going to be in parallel. So if one of them is shaded, this will have access to this one panel and will optimize whatever power it can take from this, and it's not going to affect the power extraction from the rest of the panels. So this way, what we're maximizing the power extraction from all these panels. And that's how you see these power electronics are helping us to get more energy out of this. You may think that we will replace one inverter with so many inverters. Does that make sense? It kind of makes sense. The reason is that these inverters are going to be very small, and we're going to try to make it as small as possible. So you can see this is Sunny Boy string inverter. If we had a central inverter, it would be like, I don't know, 10 times this probably. But this is a string inverter. This is a micro inverter. This is an optimizer. I didn't talk about it. We don't have time to go into that. And this and this are called integrated AC modules. So now we're going inside the module, and we're trying to actually make a chip that gets integrated inside the PV cells and optimizes the power taken from each cell. That way, whatever is shaded is going to be optimized, and the rest of the system is going to just operate as they were doing before. And that's where the power electronic is going. It's trying to, this is, if you look at it, this is the same trend that we saw maybe 45, 50 years ago in electronics. They had these transistors, discrete transistors, and over time they tried to increase the frequency, they squeezed the size, they integrated, and then until they got into the chip. We're going through the same process, but unfortunately, because now we're processing power, as you reduce the size of this chip or the converter, the loss becomes even more and more important. Just imagine, in that size chip, if you lose, even if you dissipate even a tiny amount of power, even like, let's say 0.4 watt, 0.2 watts, it's going to increase the temperature of that piece by maybe 100 degrees. So it's going to melt it because it's too small and it cannot dissipate the heat easily. And that's the challenge that we're facing, how much we can reduce the size of these converters. But there are different topologies, different configurations, and they're trying to manage this heat. They're trying to increase the efficiency so that they can they reduce the size. And right now, you can find converters with the size of a finger that can handle 1 kilowatt. So it's not too far. We're not too far from these ideal cases, but it's very, very difficult, and it's that's one of the research, many research in power electronics that are going toward this kind of, topologies. Any questions so far? So here you can also see that as this size goes down and down, the price gets down, and this is the cost per watt. So eventually these integrated chips, they should be so cheap that they will be comparable to a central converter, and it will maximize the energy efficiency of the whole system. They create lots of controllability and monitoring and, lots of control over the system. and there's the way to go. So let's talk about wind turbines. Wind turbines also, been they've been used for a long time, but how power converters are actually helping us to extract more power from the wind turbine. So this is a large-scale wind power system. You can see that normally you have the wind turbine and the windmill, and then here you can kind of control the speed with changing the pitch of the blades, so you can control what speed this is rotating, and you're going to have a gearbox, and this shaft will be the prime mover for a synchronous generator. So this synchronous generator is something that is connected to the grid, but when you rotate it, it will create some AC power at the output. But if it's connected to the grid, you should be very close to that speed, right? The frequency that you're rotating should be exactly a constant number multiplied by 60 hertz, for example. So how do you do that? You have to have this speed control and change the speed of this so that this is close. But is this okay if I just control the speed or pitch of the blades? Am I going to get all the power that was available at the moment? No, because sometimes because the wind is too fast, I can't, and my gearbox has limitations. I cannot, reduce the speed as much as I want, and these are discrete numbers, so I can go just to one level and then try to stay there. So the rest we have to change the pitch, so we're actually losing power. We're not extracting as much as power as we could. So what is the first alternative to this? We can use induction generators or synchronous generator. We can connect that to the gearbox again and wind turbine, but this time we're not worried about the grid anymore, because we say, okay, whatever you generate, synchronous generator or induction generator, it's okay. I can take that, I can convert that to DC, and then I convert it back to AC. And these power electronics will actually synchronize the output power that I'm injecting with the grid. So this grid, the grid and the synchronous generator and the wind turbine speed are now decoupled, which means they can go at a different speed. And now I can actually change the pitch so that I can get the maximum power available from the wind turbine. So this is one simple alternative, and you can see how power electronics is used to help us to get all the power that we can get. Probably in one of the courses here, you're going to do some kind of simulation for the whole, a simple system like this for the whole system, how to control this and all those things. Anyways, this is another application of power electronics in renewable energy systems. Questions so far? No? All right. So what are the requirements and trends? If you look at it, you can see there are many different important factors. Costs are important, really important. The failure rate is important, volume is important, weight, losses, time to market, how complicated the converter is. So if you look at this, you can see this is where we are at a specific volume, weight, losses, and everything. Where do we want to be we want to reduce all of this. We want to reduce the volume, the weight, the losses, time to market, cost, failure rate. And this is a complete good picture of what you desire and what these power electronic designers are trying to do. So one person may be able to create very good topology, nice operation and everything, but when you look at it, you see, the time to market, the complexity is too high, or it's too sensitive, the failure rate can be high, so it's not just optimizing one of these. We want to optimize all of them and bring down all of them. In one specific application, one of them might be critical. Let's say in aerospace applications. In aerospace applications, whatever you put in a shuttle, by grams, it's important. So if you design a converter 1 gram higher or lower, it's going to make a big difference. So they will have lots of discussions that, okay, this converter can't be this. It has to be, let's say, 10 grams lower. So the volume can be very, very important in that application because the space in the shuttle is limited. But the cost is not that important because they're going to just build a few of them and done, right? So they don't care if you have a topology that costs $10,000 for a simple buck converter, but as long as it takes the minimum volume and minimum weight and losses and also failure rate, they're happy. But in other applications, let's say consumers, let's say a charger for your computer, costs are very, very important. Time to market is even more important. So volume weight, that can be a good business case for the marketing people to go out and say, the power supply I'm designing is better than yours because it has a better volume and weight, but you cannot discuss with others and say, the cost is like the cost of your computer, but my volume is low, so they don't accept it, right? So that's why it becomes very complicated to design a power converter for each one of these different applications that we discussed. Here you can see they come up with so many different ways to reduce the size. This is a 10 kilowatt high power density 3-phase AC/DC AC converter, and this is 50 watt 80 ampere brick. It's by Vicor, and the same company now I mentioned to you can create, is producing the 1 kilowatt almost chip size converters. So what are the other applications that these days are important, and you can see them everywhere, like hybrid electric vehicles? Why do we need so much power electronics there? If you look at a hybrid vehicle, you can see that you have the engine, but also you have some electric motor. They're coupled and they can help each other. So you need some power electronics to drive this electric motor so that you can save some energy. You have this battery pack and a charger. So when you're at home, you can plug it in and charge the battery. How can we save the energy? If you look at this diagram, you can understand. So you have this engine that is taking the gas from the tank. So this black arrow shows the normal operation. It's like a normal car. You have the engine, and that engine is rotating the car. How does it do that? Right now, it's through generators. The power goes through AC/DC, inverter, motor, and then that rotates this. Or maybe the engine can directly, be applied to the tires. But now let's say you don't have gas or you don't want to use that. So the battery can help. You can take the power from the battery. So it will be which mode? So it will be, I guess, so it's saying that the normal operation, you can also take, that's how they defined it. You can take the power from both the battery and also from the battery packs. In regenerative braking, it's saying that you can, as soon as you brake, the energy that you have in as inertia is stored in the machine, in the car, because it's moving. That energy can be converted back to electrical form and can be fed back to battery. So it's charging back the batteries. So how is that done? By operating the motor that you have in generator mode, and that can take back the energy from mechanical to electrical form and charge back these two. Or if you have idling, even the engine is not doing anything, you can see that the power can go from the generator, it can go to the batteries. So the engine is turning, that can turn the generator, and instead of just wasting that, because if in a normal case the engine is turning, you didn't stop the car, the engine, you just stop behind the red light. So that energy is going to the generator, going to the AC/DC converter, and it's just charging the battery. So you're not wasting that gas and that movement, the mechanical movement. And the EV mode, that was the one that I was looking for. In EV mode is when you don't have the gas, you can only take the power from the battery. So let's say the gas is done, so you get the power from there through the inverter, and then through the motor you drive the car. So you can see that you're managing the power flow, right? Where the power is coming from, how it's being delivered, is going back. How did we do that? Again, with the help of inverters and converters and all the control system, the energy management system that we have here. So again, this gives you another good example how these power electronics are used. Each one of these applications will have specific problems, specific challenges. And if you start working on one of those, you'll be spending a long time before you can feel that you know everything about that specific application. Because there are lots and lots of technical details in each one of these applications, and how to design the converter and control systems. One of the obvious ones is like how these converters are used, where they're placed. For example, in lighting systems, when you have LEDs, you also need some power electronics there. Or ballast system, you may have some power electronics to light up the fluorescent lamp. So how does that happen? You have to have these power electronics right in the back of this LED or fluorescent lamp. So you're putting this converter piece of electronics in very hot and confined space. So it means the temperature they're working and the space that you have to design this, and specifically the cost for this is going to be extremely important. In lighting applications, if you look at the specific things, the converters, even one resistor or MOSFET is going to make a difference in the total cost. So they're very, very cautious about how many components are going to be used, because millions of these are going to be produced and used by consumers, and there's a war between all of these companies to give you a better price. And at the end of the day, the converter has to be very simple but very reliable, and also very harsh environment to operate, small and hot, just because it's very close to the lamp itself or to LED arrays. This is again another explanation how this converter is running or driving this lamp. As you know, you need a high voltage here, but at the same time you need, especially for lamps, you need very nice low harmonic current. So this power converter that you have probably has 2 stages or integrated 2 stages, and a rectifier and an EMI filter. So voltage will go through this, and this current is shaped again by PFC, so it's sinusoidal so the current that you see on the line here will be almost sinusoidal, but at the end, this converter, resonant output converter, is going to create very high voltage at the beginning so that the lamp starts, and then it will reduce the voltage so that it can operate normally. The same thing that just a normal ballast system does. So this is electronic ballast. So when you see, again, a few important things, you see some conversions, different types of conversion for different reasons, and complicated controls for all of them to make sure that each one of them is doing what they're supposed to do. They're doing their jobs and duties. So what is the grid and utility applications? These are, you've heard about smart grid and all those things. This is what's called the smart grid 2.0. And what they're thinking is to create cities or grids that have all sorts of flexibility and converters in it. You can see that you have distributed energy resources, you have internet everywhere, so all of these components are going to talk to each other. They will communicate to optimize the energy. You will have centralized or even distributed energy storage, energy management systems. You would have energy efficient buildings with connected through converters with others. You have discrete cooling and interruptible loads, those ones that you can turn off when there's not enough energy or the energy cost is too high, and then turn them back, the ones that operate on batteries. So all these different things can be connected and controlled. This power flow throughout this system can be controlled through all kinds of power converters along with a strong communication system. So when you look at this, you'll see that how complicated this can be, especially when you dealing with so many different power converters that each one of them have a different objectives and trying to shape the voltage current and in their own way to reach to their objectives. But overall, this is where we're going. This is what they're planning to do to increase the reliability, to decrease the cost, and to reduce the pollution and everything. So this is a good picture taken from this source. You can read more about this, grid applications in there. This is another one, solid state transformer, they call it. So in a normal distribution system, you will have, the generation, and you go to transmission systems, different substations, different voltage level. The voltage level comes down. So this is a normal transformer. And at some point, they're thinking, and this is getting to some commercialized level, that they're using solid state transformer, which means solid state is like power electronic based transformer. So you can think about it as like AC to AC converter. So this AC to AC converter is like a transformer, but you can control either side. A transformer, you apply voltage there, you get an output voltage and it will transfer the power. There's no control there. But with a solid state transformer, you can just replace it with a normal transformer. They can reach to even lower volume and better efficiencies. And you can place it in different locations to connect different things to each other. For such systems, you don't have to have everything in AC. And the problem with AC is that it has so many losses involved in AC systems. And now that we have power electronics, we can actually use the advantage of DC. And many of the resources that we have, renewable resources, they directly generate DC, like fuel cells, the battery, the PV panel. They're all generating DC. So when you want to connect those to AC system, you need this extra stage, which means extra losses to connect them to AC. So now you can think about a house which is running all on DC. So for those houses, you can directly have this kind of transformers. Doesn't matter, on one side it can be AC, on the other side it can be DC. And it can feed all these houses. Or they can feed also a normal house. So it can be a mix of source load ecosystem and with no problem. And that's, again, another line of research that people are moving and working on to get a better, overall efficiency and controllability of power flow throughout the grid and a utility. Any questions? Yeah, I think that was my last slide. We're almost, we're a few minutes early, but I'm not gonna start the lectures. Try to go over the material that I posted on eClass. These were what I explained today was to just give you some idea about energy systems, power electronics, where you want to go, what you want to do, and give you some better understanding of the whole research areas. But in the course, we're not going to talk about specific applications too much. We're going to focus on the converters. We're going to get into very basics and details and try to get an optimal design of the converter. But again, that converter can be, that technique that you learn can be applied to any converter. All right, if there's no other questions, this is the end of it. We can say goodbye. We can see each other next week. I will stop the sharing and I'll stay here if you have any questions. Thank you.
Okay, thank you. Bye-bye.
Bye-bye.
I just had a question for the project.
Yes.
So, as you stated that the project is it's a whole term project, and are you going to be posting a list of what kind of converters we can work on, or are you going to be assigning different converters to each student so they can work on them?
I will assign converters to students.
Okay, so then for now, for like this coming week, is there anything that we should be working on ahead of time? Because as you know, it's time constrained.
No, don't worry about that. We will get there. You have to learn a few things before we get there. So I'm not going to confuse you with, giving you something ahead of time. We will go step by step. So First, probably you're going to see some basics, as you will see next week, even as basic as talking about power calculations, waveforms, basics of converters, even, heat sink design, those kind of stuff. And then we're done with all those basic background things. We'll talk about steady state analysis, and when we get there, then I'll post the first converter, and I'll ask you to follow. The main reason is that I want you to first focus on learning what you're learning and applying it to your assignments. Make sure the basics are covered. And when we get to that point that now we can apply the technique to a converter, we'll assign the converters and you can start.
Makes sense. So, like, for example, I was in your 401 class last semester. So the buck boost and all that. So first we're just going to go through all the basics on 401, and then we will work and apply those on the power converter.
I'm not going to go through all of them, but
main ones required for this course.
Yeah, we will talk about some of them, but we will talk about more details that we didn't talk in that course. For example, we talked about buck converter, but we didn't talk about how to design a buck converter.
Makes sense, yes.
What happens if I have some parasitic components? And then how to analyze a converter. It doesn't matter if it's a buck converter, boost converter, or any converter.
Makes sense.
Procedure, step-by-step procedure that you can follow to actually analyze any converter, right? So when you learn that, then you can start applying that to a new converter. Although you know the basics of this analysis and everything, if I give you the converter right now, most probably you're going to get stuck because you've learned in that course just to analyze a converter with one switch.
Makes sense.
Now, what happens if you have more than one switch? What happens if you have more than one passive component? It becomes very confusing. So
yes.
First I have to introduce that formal analysis method, and then you can apply it to any converter.
Okay, perfect.
Yep.
That makes a lot of sense. Thank you so much.
Yep, no worries. Hello, do you have any questions? Okay, it seems like you've pressed the record and gone.